Somewhere above the disk of our galaxy, far beyond where most stars ever wander, something is moving in a way stars aren't supposed to move. It isn't orbiting anything, it isn't circling back, it's leaving. Not drifting slowly outward over billions of years, the way you'd expect from the slow gravitational churn of a galaxy. It's racing away right now, at a speed so extreme that if you tried to imagine a bullet leaving a rifle as slow by comparison, you wouldn't be exaggerating by much. Astronomers pointed the Hubble Space Telescope at it, expecting to confirm a curiosity. What they got instead was a star with no business existing where it was found, moving in a direction that shouldn't have been possible, at a velocity that broke the ordinary rules of how stars are supposed to behave inside a galaxy like ours. Picture the Milky Way the way most of us imagine it, a vast, slow-turning pinwheel of light, every star locked into its own patient orbit, circling the galactic center the way planets circle a sun. Nothing rushes, nothing leaves. It's a closed system, self-contained, the same 100 billion stars endlessly retracing the same paths for billions of years. That picture is wrong, or at least it's incomplete, because somewhere in that quiet, orderly pinwheel, a small number of stars have stopped following the rules entirely. They aren't circling anymore, they're running. And once astronomers realized what they were looking at, they had to ask a question nobody had seriously entertained before. How does a star get kicked out of its own galaxy? Where does that kind of violence even come from? And once they finally traced one of these runaway stars back to where it began, why did the answer only raise more questions than it solved? Today we're going to follow the evidence, star by star, discovery by discovery, the way the scientists themselves had to follow it. One clue at a time, with no guarantee the pieces would ever fit together. We'll look at what Hubble actually saw. We'll walk through the competing explanations astronomers have proposed for it. We'll see where those explanations broke down, and why. More than a decade after the first hypervelocity star was found, scientists are still arguing about where some of these strange escapees actually come from. Because it turns out the Milky Way has been quietly launching stars into intergalactic space for a very long time, and we've only just started to notice. To understand how strange this really is, you have to understand what a galaxy is actually doing to every star inside it, all the time, without exception. Our galaxy is not a static picture. It's 100 billion stars, give or take, locked in a slow, patient orbital dance around a common center of gravity, the same way planets orbit a sun, just on a scale that swallows the imagination. The Milky Way's disk alone stretches roughly 100,000 light-years across. Our own solar system takes about 225 million years to complete a single lap around the galactic center, cruising at roughly 500,000 miles per hour as it goes. That's our normal. That's what every star, including our sun, does, quietly and forever, bound by gravity to the collective mass of the galaxy around it. To break free of that, to actually leave the Milky Way rather than just riding it around in an endless circle, a star doesn't just need to be fast, it needs to be moving so fast that the entire gravitational pull of 100 billion stars, plus an enormous unseen halo of dark matter wrapped around all of it, simply isn't enough to reel it back in. Astrophysicists have a number for this. It's called the galaxy's escape velocity, and depending on where you are in the Milky Way, it sits somewhere above 1,000,000 miles an hour. For comparison, that's roughly 2 to 3 times faster than the sun's own orbital speed. It's not a small bump in velocity, it's an entirely different category of motion. To put the difference in scale, think about what actually holds a star in orbit in the first place. It isn't just the visible stars around it. Astronomers have known for decades that galaxies like ours are wrapped in an enormous, invisible halo of dark matter. Matter that doesn't emit or reflect light, but whose gravity is very much real, and which outweighs all the visible stars in the galaxy combined. Any star trying to escape isn't just fighting the pull of 100 billion suns, it's fighting the pull of that entire hidden halo too. Reaching escape velocity here isn't like a rocket clearing Earth's atmosphere. It's like clearing the gravity of an entire galaxy's worth of matter, most of which we can't even see directly. So here's the first real question. What in a galaxy built on slow, stable, billion-year orbits could possibly throw a star hard enough to break that rule entirely? For a long time, astronomers didn't think it happened at all. Stars were born, they lived, they orbited, and eventually they died, all while staying gravitationally bound to the galaxy that made them. The idea of a star simply leaving, permanently, irreversibly, at a speed nothing natural should produce, sounded almost like science fiction. Then, in 2005, an astronomer named Warren Brown, working at the Harvard Smithsonian Center for Astrophysics, found the first one. It was a star with an almost absurd velocity, moving at over 1.5 million miles an hour relative to the rest of the galaxy. Fast enough unambiguously to escape. Brown hadn't set out looking for it specifically. He stumbled into it while surveying faint blue stars in the galaxy's outer halo. But once the number came back, there was no ambiguity about what he was looking at. This star was leaving, and it wasn't coming back. Over the following years, Brown and his colleagues found more. By the early 2010s, they'd confirmed around 16 of these so-called hypervelocity stars, all moving fast enough to escape the galaxy entirely. Brown himself was responsible for finding most of them, methodically searching through faint, distant blue stars in the galaxy's halo, a region where you wouldn't expect to find young, hot stars at all, since stars that color en masse tend to form and live out their short lives much closer to the crowded galactic disk. That in itself was part of what made the search possible. A young blue star sitting alone in the sparse, quiet outer halo, far from any stellar nursery that could have produced it, is already a small anomaly. Brown and his colleagues used exactly that oddity as a search strategy, treating every out-of-place blue star in the outer galaxy as a candidate, then checking its velocity to see whether it was simply a wanderer or something that had been thrown. Every hypervelocity star discovery raised the same underlying question, though. Fast is one thing, but what specifically could push a star hard enough to reach these speeds in the first place? Ordinary stellar processes, supernova explosions, close stellar flybys, the gradual pull of orbital dynamics, simply don't produce velocities in this range. Whatever mechanism was responsible had to be something rare, something violent, and something capable of delivering an enormous amount of energy to a single star in one sudden event. But here's where the real mystery starts, because finding a fast star is one thing. Explaining why it's moving that fast is something else entirely. The leading theory, first proposed by astrophysicist Jack Hills back in 1988, almost 2 decades before Brown's discovery, involves the one place in the galaxy violent enough to produce this one, the supermassive black hole sitting at the Milky Way's very center, a gravitational monster with a mass equivalent to about 4 million suns. Here's how the mechanism is supposed to work. Imagine a binary star system, 2 stars locked in neutral orbit around each other, wandering too close to the black hole. The black hole's gravity is so extreme that it can rip the binary pair apart. One star gets captured, pulled into a tight orbit around the black hole, or swallowed entirely. But the other star doesn't just disappear. In the violence of that separation, it gets a gravitational slingshot kick powerful enough to send it rocketing outward, away from the galactic center, at speeds far beyond anything a star would ever reach naturally. It's an elegant explanation. It's also, on paper, testable. If the Hills mechanism is really what's flinging these stars outward, then every hypervelocity star should trace back, in a straight line, to one specific point, the center of the Milky Way. This is where Hubble enters the story, because measuring a star's speed is one thing. Spectroscopy from ground-based telescopes can do that by analyzing how a star's light stretches and compresses, the same Doppler effect that changes the pitch of a siren as it passes you. That technique tells you how fast a star is moving toward or away from Earth along our line of sight. What it can't tell you is which way the star is actually heading across the sky, and that's the piece of the puzzle that actually matters if you want to know where a star came from. To get that, astronomers need to measure something called proper motion, the almost impossibly small sideways shift of a star's position against the fixed backdrop of far more distant stars, tracked over months or years. For a star tens of thousands of light years away, that shift is unimaginably tiny, a fraction of an arc-second, the angular equivalent of watching a coin from miles away, and trying to detect that it moved by the width of a human hair. Ground-based telescopes, fighting through the blur of Earth's atmosphere, struggled to measure it with any confidence. It was for years considered nearly impossible to do reliably from the ground, for a target this faint and this far away. Hubble, sitting above the atmosphere entirely, could do it. In 2010, astronomers pointed Hubble at a hypervelocity star called HE 0437-5439, one of the fastest ever found, blazing outward at roughly 1.6 million miles an hour. Where Sparsenmods of first and worst and second stir and surster, where station immersion surgeons nods emerge about 3 times faster than our own sun's orbital speed around the galaxy. This star was already about 200,000 light-years from the galactic center, out in the Milky Way's distant, sparsely populated outskirts, far beyond the edge of the visible disk. And there was an immediate problem with it, a problem that, for a while made scientists doubt the Hill's mechanism might apply here at all. The star's mass and color suggested it was a young blue star, the kind that burns through its fuel fast and dies within about 20 million years. But its distance from the galactic center told a different story. If this star really had been launched from the Milky Way's core, traveling at its observed speed, the math said it would have taken roughly 100 million years to get to where it currently sat. A star that should have died 5 times over, drifting through space 100 million years after it should have burned out. That's not a rounding error, that's a direct contradiction. So what was actually going on? Was this star not from the galactic center at all? Had the Hill's mechanism completely failed to explain it? Or was something else happening that nobody had accounted for? This is where the investigation could have gone several different directions, and for a while it genuinely wasn't clear which one was correct. One possibility: the star wasn't launched from the center of the galaxy at all. Some astronomers had already floated the idea that certain hypervelocity stars might instead originate from the Large Magellanic Cloud, a satellite galaxy orbiting the Milky Way, which could have its own internal ejection mechanisms entirely separate from our galaxy's central black hole. If that were true here, the timeline problem might resolve itself. Different point of origin, different distance, different math. Another possibility: the star really was ejected from the galactic center, but the assumption about its age was wrong. What if this wasn't an ordinary young blue star at all, but something rarer? A blue straggler, a star that looks young and blue not because it recently formed, but because it's actually the product of 2 smaller, older stars merging together, resetting its apparent age in the process. If that were the case, its true history could stretch back much further than its appearance suggested, long enough to match a 100 million year journey from the galactic core. When Hubble's proper motion measurements came back, they settled at least one part of the debate, decisively. The star's direction of travel pointed directly back to the center of the Milky Way, not approximately, not roughly in that general direction, directly. This was, at the time, the first direct observational link connecting a hypervelocity star to a galactic center origin, rather than an origin merely inferred from statistics and probability, which meant the blue straggler explanation had to be correct. This star likely began as part of a triple star system, 3 stars orbiting close together that wandered too near the supermassive black hole roughly 100 million years ago. One member of that trio was captured or destroyed. In the chaos of that encounter, the remaining 2 stars, already orbiting closely together, were flung outward together, retaining enough shared momentum to eventually merge into a single object, hotter, bluer, and younger looking than its actual age would suggest. A star born from violence twice over. Case closed, right? Hubble had confirmed the mechanism. The math worked. The star's motion pointed exactly where theory predicted it should. Except that wasn't the end of the story. It was barely the beginning. Because if every hypervelocity star really did originate at the galactic center via the same violent black hole-driven mechanism, then every single one of them, without exception, should trace back to that same origin point when astronomers checked their motion. They don't. In January of 2014, a team of astronomers led by Lauren Palladino at Vanderbilt University, working under astronomer Kelly Holly Bockelman, was mapping the orbits of sun-like stars using data from the Sloan Digital Sky Survey, an enormous survey covering nearly a quarter of the entire sky. They weren't specifically hunting for hypervelocity stars, but buried in that data, they found 20 of them anyway, ordinary sun-sized stars moving fast enough to escape the galaxy's gravity entirely. And when they traced these 20 stars backward, none of them pointed toward the galactic center, not one. This should not have been possible if the Hill's mechanism, involving the central supermassive black hole, was the only way to produce a hypervelocity star. As Holly Bockelman put it at the time, it's extraordinarily difficult to kick a star out of the galaxy at all. The accepted mechanism required tracing back to the galactic core, and these 20 stars flatly refused to do that, which meant one of 2 things. Either there was an entirely different mechanism at work, one nobody had previously identified, capable of launching stars to escape velocity without any involvement from the central black hole at all, or these 20 candidate stars weren't really hypervelocity stars, and something in the data or the analysis needed a second look. This is the point where a good investigation has to slow down and separate what's actually been observed from what's merely been inferred. What had been directly measured was the stars' velocities, calculated from their position and motion within the survey data. What remained genuinely uncertain, and still does for much of this population, was the precision of those measurements at such extreme distances, and the exact point of origin for stars whose backward trajectories don't point anywhere obvious. Scientists studying this new population have proposed several candidate explanations since, and each one comes with its own strengths and its own holes. One points toward the possibility of ejection through close encounters with other massive objects scattered throughout the galaxy's disk, dense star clusters, or massive binary systems, capable of producing their own smaller-scale gravitational slingshots without any involvement from the central black hole at all. It's a plausible mechanism in principle, but it struggles to explain why so many of these sun-like escapees would need such a specific, relatively rare kind of close encounter to reach such extreme speeds. Another points toward the Milky Way's satellite galaxies, not just the large Magellanic Cloud, which orbits our galaxy at a distance of roughly 160,000 light-years, but smaller, more fragile structures like the Sagittarius dwarf spheroidal galaxy, a small companion galaxy that has been getting torn apart by the Milky Way's gravity for hundreds of millions of years, leaving long streams of stars trailing behind it like debris off a ship. In 2020, a separate group of astronomers published a candidate hypervelocity star, whose trajectory, when traced backward, pointed not at our galactic center at all, but toward the Sagittarius dwarf's own path through the sky, raising the possibility that this small, doomed satellite galaxy has its own way of flinging stars outward as it gets shredded by our galaxy's gravity, whether through its own central black hole, if it has one, or simply through the violent tidal forces tearing it apart. Both explanations are attractive for a similar reason. They don't require inventing new physics, only recognizing that the galactic center isn't the only violent neighborhood capable of producing a hypervelocity star. But neither one, on its own, cleanly accounts for every star in the second population. Some don't point convincingly toward the Sagittarius dwarf's path either. Some show no obvious connection to any known cluster or satellite structure at all, which has left open a less satisfying but scientifically honest possibility that this second population isn't the product of one single mechanism, but several different ones, overlapping and tangled together, each contributing a handful of stars to a category that only looks unified because all of them happen to be moving fast enough to leave. None of these explanations are settled. That's important to say clearly, because a documentary like this one could easily slide into treating an interesting hypothesis as a confirmed answer. It isn't. What's confirmed is that this second population of hypervelocity stars exists, and that their trajectories don't match the one mechanism that had, until then, explained every previous case. What remains a hypothesis is exactly which alternative mechanism, or combination of mechanisms, is actually responsible, and the mystery didn't stop growing there. In 2024, astronomers using ground and space-based observations identified something even stranger, a hypervelocity star far smaller and dimmer than any of the blue giants that had defined the category for nearly 2 decades. This one was a low-mass L subdwarf, a small, cool, faint star, the kind that's usually far too unremarkable to draw much attention at all, except this one was racing across the Milky Way on a trajectory that may eventually carry it beyond the galaxy entirely. That discovery matters because it suggests hypervelocity stars aren't a rare, narrow category limited to a handful of dramatic blue giants ejected in one violent encounter near a black hole. They may represent an entire spectrum of stellar sizes, ages, and origins, hiding in plain sight across an enormous range of the galaxy, most of them faint enough that nobody had thought to look for them until relatively recently. Think about the search strategy that had worked so well for Warren Brown years earlier, hunting for bright young blue stars sitting somewhere they had no business being. That strategy only works because those stars are relatively easy to spot. A faint, cool, low-mass star doing the exact same thing, escaping the galaxy at the exact same kind of extreme velocity, is far harder to notice in the first place. It doesn't stand out. It doesn't look out of place in a survey image. The only way to catch it is to measure its motion directly, star by faint star, across an enormous number of candidates, and hope the right one happens to be moving fast enough to matter, which raises an uncomfortable, exciting possibility. If the classic blue hypervelocity stars were only the most visible, most dramatic tip of this phenomenon, then the true scale of stars escaping the Milky Way might be dramatically larger than the current catalog of a few dozen confirmed examples suggests. Not a rare exception, possibly a steady, ongoing leak that's been happening for as long as the galaxy has had a supermassive black hole. satellite galaxies being torn apart, and dense stellar environments capable of producing these violent gravitational slingshots. We simply haven't had the tools until very recently to notice most of it happening. So where does that leave the picture as a whole? What do astronomers actually know with confidence right now, and what remains genuinely open? Here's what's established. Stars really can, and do, escape the Milky Way entirely, reaching speeds well beyond the roughly 1 million mile per hour threshold required to break free of the galaxy's combined gravity, including its enormous, largely invisible halo of dark matter. Hubble's precision measurements of at least one hypervelocity star, HE 0437-5439, directly confirmed a trajectory pointing straight back to the galactic center, strongly supporting the Hill's mechanism, a close encounter between a multi-star system and the supermassive black hole at the Milky Way's core, as at least one real, physically demonstrated way this happens. Roughly 24 or so of these classic blue hypervelocity stars have now been identified through exactly this kind of mechanism. And here's what's still an open question. A second population of hypervelocity stars, first identified in significant numbers in 2014 and expanded upon since, doesn't trace back to the galactic center at all, and the mechanism responsible for launching them remains genuinely unresolved. Competing explanations point toward interactions with other massive structures inside the galaxy, or ejections tied to the ongoing destruction of satellite galaxies like the Sagittarius dwarf. Neither has been confirmed as the definitive answer, and it's entirely possible that more than one mechanism is operating simultaneously, launching different stars under different circumstances at different points in the galaxy's history. We also don't fully know how common this phenomenon actually is across the galaxy's full history. The known hypervelocity stars represent an extraordinarily small fraction of the Milky Way's roughly 100 billion stars, by some estimates, something on the order of 1 in every 100 million. But that number is built entirely from what astronomers have managed to detect so far, using surveys and instruments that are only sensitive to certain kinds of stars, at certain distances, moving in certain ways. The true population, including fainter stars like the low-mass L subdwarf, found in 2024, may be considerably larger and considerably more varied than the current catalog suggests. Future instruments may finally settle some of this. The European Space Agency's Gaia mission, which has spent years precisely mapping the positions, distances, and motions of over 1 billion stars across the galaxy, is providing exactly the kind of large-scale trajectory data needed to catch more of these escapees and trace their origins with far greater statistical confidence than smaller targeted surveys ever could alone. Where Warren Brown's original searches relied on painstakingly identifying individual candidate stars one at a time, Gaia's approach is closer to casting an enormous net across the entire sky at once, measuring the motion of over 1 billion stars simultaneously and letting astronomers sift through that ocean of data for anything moving fast enough to qualify. That shift in approach matters because it changes the kind of question astronomers can ask. Instead of searching for the next single hypervelocity star, they can start asking population-level questions. How many hypervelocity stars, in total, does the Milky Way currently contain? What fraction trace back to the galactic center versus some other origin? Whether the second population, the one that doesn't point back toward Sagittarius A star, actually shares a common origin at all, or whether it's really several unrelated phenomena that happen to produce similar velocities. Combined with Hubble's ability to nail down fine, high-precision details for individual targets once Gaia flags them as candidates, and future observatories built specifically to probe the crowded, dust-obscured region around the galaxy's actual center, astronomers expect the population of confirmed hypervelocity stars and the range of mechanisms responsible for them to keep expanding for years to come. Some of the biggest open questions in this field may not get resolved through a single dramatic discovery, the way HE 0437-5439 briefly seemed to settle things back in 2010. They may get resolved slowly through the patient accumulation of thousands of smaller data points, each one narrowing the possibilities a little further, the same unglamorous incremental process that built this entire field of study in the first place. There's something worth sitting with once you step back from all the individual measurements and competing theories. Every star in the sky that you can see with your naked eye is bound to this galaxy, locked into an orbit that will carry it around the galactic center for as long as it exists, the same slow, patient loop our own sun has traced for billions of years. and we'll keep tracing for billions more. That's the rule. That's how galaxies work. That's how stars are supposed to behave. And yet, scattered across the Milky Way, invisible to the naked eye but unmistakable to instruments like Hubble, there are a small number of stars quietly breaking that rule completely. Stars that found themselves through violence or chance or a combination of forces we don't yet fully understand, moving fast enough to simply leave, not orbiting further out, not drifting toward the edge over some unimaginable span of time, actually leaving on trajectories that will eventually carry them out of the galaxy entirely, into the vast, mostly empty gulf of space between galaxies, where they'll continue traveling essentially forever, untethered from the gravity that shaped every other star around them. Somewhere out there, right now, stars we've already found, and countless others we haven't yet noticed, are making that same journey. A star that spent millions or billions of years as part of an ordinary orbiting family of stars, suddenly finding itself flung into a one-way trip toward true isolation, carrying whatever planets or history it once had along with it, into a darkness with no return path and, as far as anyone currently knows, no true destination. We used to think of the Milky Way as a closed system, 100 billion stars, gravitationally bound, cycling forever around the shared center. What Hubble and the astronomers who followed its data outward actually found is something quieter and stranger than that. Our galaxy isn't entirely closed, it's leaking, slowly, star by star, into the space beyond it. And we've only just begun to notice and to ask why. It's worth remembering that on the scale of a galaxy, 100 million years, roughly how long HE 0437-5439 has been in flight, is barely a passing moment. That star left the crowded, violent heart of the Milky Way when dinosaurs still walked the Earth, and it has been traveling alone in a straight line ever since, entirely indifferent to everything that has happened back home. It will keep traveling long after our sun has swollen into a red giant, and the Earth itself has been consumed. It is, in a very real sense, one of the most durable things our galaxy has ever produced, not because it's special, but because it's finished. It has nothing left to interact with, nothing left to pull it back. And somewhere out past the edge of what any telescope has mapped in detail, more of these stars are quietly making the same crossing right now, unnoticed, simply because nobody has pointed the right instrument at the right patch of sky yet. Every hypervelocity star we've found took years of careful, patient measurement to confirm. Every one we haven't found is still out there, moving. Maybe that's the real shape of this discovery, not a single dramatic escape, but a slow, ongoing leak that's been happening for as long as the galaxy has had a violent enough center to produce it. Stars slipping past the edge of what we consider home, one at a time, largely unnoticed, until an instrument sensitive enough finally happened to be looking in the right direction. The Milky Way has been letting stars go for longer than humans have existed to watch it happen. We've only just learned how to see them leave.